Hi everyone! Today we are going to be covering a few topics and building on some of the Ekman concepts we have talked about in class so far. First we'll be deriving Ekman transport, which is the net effect of the Ekman spiral we talked about in class on Thursday. Then we'll discuss the role Ekman plays in ocean circulation, and we'll talk about Ekman pumping and the upwelling and downwelling associated with that. We'll follow by discussing relative, absolute, and potential vorticity, and finish by talking about sphere jet transport and the total response of the ocean to wind below the Ekman layer. Alright, so quickly I want to go through the Ekman transport derivation. We discussed Ekman transport in class, which is the net effect of the Ekman spiral, and moves the upper ocean 90 degrees to the right of the surface stress, or wind stress. Let's say our wind is blowing in the x direction, so we start with our equation discussed in class for the wind stress. If we recall the Ekman balance, we are left with these two terms from the momentum equations. If we set these equations equal to each other, we have the mass equal to 1 over the Coriolis force times d tau dz. Again, the wind stress is in the x direction in this case. So to get the net effect, we want to integrate mass transport over depth. We'll label the net effect as m, and since our velocity is in the y direction, this will be the net effect in the y direction. So first we'll integrate the mass from the surface to the depth. Here I arbitrarily use negative infinity, but you can also use negative h or some other depth as long as it's deeper than the Ekman layer. When we integrate the left-hand side, we also need to integrate the right-hand side over the same depth. My is therefore equal to 1 over f times the wind stress in the x direction at the surface minus the wind stress in the x direction at depth. Tau x at the surface is simply just the wind stress, which is tau x. And at depth, the water does not feel the effect of the wind stress, and therefore this term is equal to 0, and we get the net effect is equal to negative tau x over f. So our net effect of Ekman in the y direction is equal to the wind stress in the x direction over the Coriolis force. In the x direction, mx is equal to the integral from the surface to depth of the mass rho u, which is equal to the integral of 1 over f times d tau y dz. Once again, this is equal to 1 over f times tau y at the surface minus tau y at depth. And in this case, we don't have wind stress in the y direction, so both these terms are equal to 0, and therefore mx is also equal to 0. And so we have my, the net effect of Ekman in the y direction, is equal to negative tau x over f. And in the x direction, the net effect is 0. This is Ekman transport, and we can see here that wind stress in the x direction only acts to move water in the y direction. Therefore, our overall transport works to move waters 90 degrees to the right of the wind stress in the northern hemisphere and 90 degrees to the left in the southern hemisphere. Okay, so just to plug some numbers in here and determine a typical value for my, recall our equation for tau, the wind stress. And suppose we have a 20-knot wind, which is approximately equal to 10 meters per second, and the wind is blowing to the east. Our drag coefficient can be estimated to around 10 to the negative 3, and we can plug the numbers in and get an approximate wind stress to about 10 to the negative 1 kilograms per meter second squared. We'll plug into my and assume we're at some mid-latitude, and we'll plug in our values for tau x and f to get negative 10 to the 3 kilograms per meter second. So in class we calculated a typical value for Ekman depth and found that at mid-latitudes Ekman depth can vary between about 50 and 100 meters. So it's important to note that Ekman is an upper ocean process and very confined to the surface waters. However, Ekman does play a significant role in ocean circulation below the depth of the Ekman layer and induces either upwelling or downwelling. We call this Ekman pumping. So we know that winds vary spatially over the ocean, and this creates convergences or divergences of Ekman transport at the sea surface. And we can visualize this with an example of when wind varies horizontally or in the y direction across the sea surface. To visualize this, imagine we have our three-dimensional ocean here. We have a gradient in our wind stress in the y direction such that the wind is stronger at y2 than at y1. Because our net transport is dependent on the magnitude of the wind stress, the Ekman transport in the x direction will also have a gradient. The transport will be larger at y2 than at y1. This will cause waters to converge within the Ekman layer, and this will drive downwelling below the Ekman layer. We can think of our w, our vertical velocity, as the gradient in transport. Our transport out, or m1 minus transport in, my2, will be negative, giving us a negative w, or downwelling velocities. We can look at general examples of this process. Note all of this is Northern Hemisphere examples. Transport will be in the opposite direction in the Southern Hemisphere. So if we have a positive gradient in wind stress, or wind stress is increasing in the y direction, our transport will diverge, leading to upwelling. On the other hand, like in the example before, if our wind is getting smaller or decreasing in the y direction, and we have a negative gradient in wind stress, the transport will build up and converge, forcing downwelling. We observe divergences and convergences with cyclonic and anticyclonic flow as well. Cyclonic wind stress forces transport out from the center, resulting in divergence and upwelling in the center. Conversely, Anticyclonic flow transports water inward, creating convergences and downwelling. Near-coast Ekman transport can also result in upwelling or downwelling. Imagine a cross-section of the coastal region. You have some bottom topography and the coastline on the right-hand side. Sorry this isn't a great drawing. Let's say winds are blowing along the coastline, sort of towards you or out of the page. The resulting Ekman transport is offshore. Those waters pushed offshore have to be replaced by upwelling, therefore bringing waters from the deep ocean to the surface. Alright, we're going to switch gears here a bit and talk about vorticity, which is a measure of the tendency of a fluid parcel to rotate. We calculate vorticity by taking the curl of the velocity field, which I'm not going to do out here, but I have done the full calculations in previous videos if you want to review. We end up with a component of vorticity in each direction. Typically, the vertical gradients in the horizontal velocity field are small, so we can neglect dv dz and du dz. The horizontal gradients in the vertical velocity field are also small, so we can neglect those terms as well. This leaves us only to consider the vertical direction. We call this relative vorticity, and we use a funny looking symbol zeta to represent it. To picture this concept of relative vorticity, imagine you have a gradient in velocity in the x direction, so that velocity is getting larger with x. Your dv dx term will be positive, and your du dy term will simply be 0. Now think about which way the columns of fluid are going to rotate. If they are subject to larger velocity on the right and smaller velocity on the left, our column of fluid will tend to rotate in this direction. If we plug in these values for our relative vorticity equation, it is apparent that we will create a positive relative vorticity, which makes sense, and we will end up with a cyclonic or counterclockwise flow. We can also define planetary vorticity, which is the vorticity due to the rotation of the Earth. This is simply the Coriolis parameter, which we call f. Together, the planetary and the relative vorticity combine to create what we call the absolute vorticity, or sometimes the total vorticity. In general, our planetary vorticity is going to be much larger than the relative vorticity. And we can see that if we compare the relative vorticity to the planetary vorticity by scaling, this is equal to U over L divided by F. This is equal to U over FL, and I hope by this point you recognize that as the Rossby number. We typically think of the Rossby number being much less than 1 for most oceanic processes, thus proving that our F parameter is much larger than our relative vorticity. Finally, we define potential vorticity. If we think about a column of fluid with angular velocity omega, height h, and density rho, the potential vorticity, or often abbreviated to PV, is equal to the absolute vorticity divided by the height of the column h. There is a derivation for potential vorticity, but it requires concepts outside the scope of this class, so I'm not going to go through it. However, there is a short section on the derivation in the reading for this week, so if you want to glance at it, you're welcome to. Conservation of PV is responsible for many of the phenomena we observe in the ocean. Imagine we have this column of fluid, and without any change in the latitude, so no change in the Coriolis parameter, the relative vorticity increases. Increasing the relative vorticity, or zeta, will want to increase PV. But since we need to conserve PV, we either need to move the water column to lower latitudes to decrease the Coriolis parameter, or increase the height of the water column, effectively stretching the column. In this case, since there is no change in latitude, an increase in relative vorticity will be accompanied by an increase in h, or stretching of the water column, to conserve PV. Similarly, as a layer of water moves from lower to higher latitude, there must be a decrease in potential vorticity or an increase in the layer thickness. If the height of the layer increases, the potential vorticity must increase or the layer must move to a higher latitude. Okay, our last topic for today is sphere drop transport, which will incorporate both Ekman and some vorticity concepts that we have talked about so far, and we will derive the sphere drop transport equation from the equations of motion and Ekman. Okay, so for some of the concepts we have talked about so far, we have assumed uniform winds in an unbounded ocean. However, we know this is not true. Real winds are not uniform, and oceans are bounded by continents. Here we have a July climatology of winds over the sea surface. Clearly we see that there are places where wind is much stronger than others. Even if we just focus in on the Atlantic, it's clear that winds vary in space, where we see the westerlies blowing from the north, above 40 degrees north, and the trade winds blowing from the east, below 40 degrees north. Clearly, winds also vary in time. Here is the same region, except here is the March climatology. We observe a much different wind field, especially in the direction of the trade winds. Over time, we see some common zonal characteristics, but also north-south shifts on a seasonal basis. Alright, so these non-uniform winds impact the surface stress on the ocean. We often observe torque, or rotational force, applied to the surface. We have convergence or divergence in the upper layer, which is just Ekman pumping that we talked about earlier in this lecture. and this Ekman pumping causes a spin up or spin down of the ocean below the depth of the Ekman layer. This is sphere drift transport, and the sphere drift is the total response of the ocean to wind stress below the Ekman layer. Before we get into this derivation, I want to explain the physical mechanisms of sphere drift transport. Here we have a three-dimensional view of the Atlantic. The trade winds blow from the east, just north of the equator, and the westerlies blow from the west. The blue arrows on the surface are the general circulation patterns of the North Atlantic gyres. In the surface layers, we observe the Ekman transport. At low latitudes, Ekman transport is north. However, the strongest transport is in the middle of the trade wind band, and therefore we have convergence at mid-latitude, or around 40 degrees north, and divergence near the equator. The same is true at high latitudes. Ekman transport is south in this case, but we have convergence at mid-latitudes and divergence near the pole. The convergence at mid-latitudes induces downwelling, while the divergence near the equator and the poles induces upwelling. Our thermocline is thus depressed at mid-latitudes and shoaled near the equator and the poles. At mid-latitudes, if the height h of our water column decreases, or the water column is effectively squashed, to conserve potential vorticity, relative vorticity either needs to decrease or the flow needs to move to lower latitudes. Since the general circulation is very large, the response is to move in latitude rather than change relative vorticity, since F is so much larger than the relative vorticity. Therefore, flow will move towards the equator, below the Ekman depth. At the equator and the pole, the opposite is true. The water column is stretched, increasing height h, and the water column will move north rather than increasing relative vorticity. Okay, now that we understand the concept of sphere drift transport, let's derive the equation from the equations of motion. We'll start with our equation in the x direction, and the same applies for the y direction, but I won't do it all out here. Recall from Ekman that we can relate our wind stress to our vertical shear, and so we can replace that term in our momentum equation. Now, as always, we'll make some assumptions about our flow. I'm going to go back and forth here so you can see which terms I get rid of with each assumption, so I apologize if it gets a little bit jumpy. First, we'll assume our viscous terms are small, since we're large scale here, and we'll get rid of the final term in our equations of motion. We'll assume steady flow and neglect the time derivative. At large scales, we can assume our Rossby number is much less than 1 and neglect the advection terms. We'll also assume our horizontal eddy terms are small compared to our wind gradients, seeing as our large-scale wind gradients that we're looking at tend to vary on scales of around 3,000 kilometers versus eddies on scales of around 100 kilometers. Excuse me. For this case, we'll also assume uniform density. And finally, the flow is indeed geostrophic. The force balance is still between the pressure gradient force and the Coriolis. The Ekman pumping is very small, and the changes induced in the vorticity are very weak. These set up the pressure gradients to drive the geostrophic flow. Remaining, we have three terms: the Coriolis term, the pressure gradient term, and our d tau dz term. We'll now integrate between the surface and some depth. Let's call it negative h for this case. Negative h is arbitrary, and it just needs to be somewhere well below the Ekman layer. Since density is constant, we'll remove rho from the bottom of each term in the right-hand side and move it to the left-hand side, and we'll integrate each term in this equation. The same goes for the y direction as well. Sorry about this here. Notice that my camera stopped recording, so I jumped ahead a term here. I'll give you a second to catch up. If we recall our equations for Ekman net mass transport, we'll remember that m is equal to the integral of mass transport over depth. Here are the equations in both y and x directions. We see that if we remove f from the integral, which we can do because f doesn't vary with depth, then we can set the equations equal to each other and plug in on the left-hand side. Now again, like in the Ekman transport derivation, we can remove the last term and recognize that tau x at the surface is the surface wind stress. We are then left with our two equations in the x and y directions. If we take the y derivative of the x term and the x derivative of the y term, we are left with the following two equations. We note that the right-hand sides are now equal, and we can set the two equations equal to each other. Now note that f does not depend on x, the longitude, but does depend on y, the latitude. So we can expand the left-hand side of this equation, being careful to use the chain rule. On the right-hand side, we can simply distribute the partial derivative and remove f to the outside. Net Ekman transport only acts in the x and y directions, and applies only in two dimensions. Thus, our continuity equation is only two-dimensional as well. Thus, this value has to equal 0, and we lose this term. Now, if we define beta as the latitudinal gradient in Coriolis, and recall the horizontal curl of the wind field, we can plug into the above equation. By moving beta over to the right-hand side, we are left with our equation for sphere-drift transport, which is the vorticity balance between wind stress curl and meridional gradient of Coriolis parameter. Alright, that's all I have for you guys today. I know this was kind of a long video, so I apologize, but this puts us in a good place for the remainder of the semester. In class on Thursday, we'll look at how sphere drift applies to western boundary currents and look at large-scale global circulation patterns, as well as finally get to see Group 4 present their Ekman demonstration. Don't forget your homework gets posted Tuesday, October 31st, and that'll be due Thursday, November 9th. Awesome. Thanks, guys. As always, let me know if you have questions or swing by my office. See you on Thursday.